In this video, we're going to talk about number theory and the undecidability of number theory and Godel's result that number theory is incomplete. Our first theorem that we want to talk about is that number theory is undecidable. Let's be clear what we mean by number theory. We're talking about the universe of natural numbers, okay, so just simple integers, and we're talking about the operations of addition and multiplication. So we limit ourselves only to simple operations, addition and multiplication. From those, using our operations of predicate logic, we can make statements, such as the twin prime conjecture. And it turns out that the set of true statements is undecidable. So given a statement from number theory, using simple operations like plus and multiplication, there is no computable procedure to determine whether the statement is true or not. Okay, we can look for a proof and we might find one, or we can look for a proof that it's not true and we might find one that it's not true, but the set of true statements is undecidable. Now, I'm not going to give the full proof, but if you follow these videos so far, hopefully you'll get the idea. The idea is simply to reduce the acceptance problem for Turing machines to the problem of deciding whether the number theory is, whether a statement is in a number is true or not, given the interpretation in number theory. So the idea behind this proof is to reduce the acceptance problem for Turing machines into the problem of deciding number theory. And since we know that the acceptance problem for Turing machines is undecidable, we can conclude that number theory itself is undecidable. In 1931, Kurt Godel proved a remarkable theory which is known as his Incompleteness Theorem. In order to explain what this is, we need to do a little background first. So let's remind ourselves what a formal proof is. It's a sequence of statements. We start with axioms, we have precise rules of inference, and we end with a theorem. Okay, this symbol here, phi, is not the empty set. Okay, it stands for a logical formula. And a proof of some logical formula we can symbolize as a sequence of statements in predicate logic, and the last statement is the statement phi that we're proving. We are assuming that the proofs are correct and that can be checked, verified. So if phi is a statement with a proof pi, and pi is a proof of that, we can check whether that is correct. In other words, given a statement and a proof, it is a computable function to determine whether that proof is legitimate and correct. Given a statement and its proof, we can decide whether that statement is a valid proof of phi. And we're also assuming soundness, that that we can only prove things that are true. In other words, if a proof exists, then the statement is true. Okay, we can't prove false things. So that's called consistency or soundness. If a proof exists, then the statement is true. Okay, these are sort of the minimum things we need for a proof system. It better be correct and it better be sound. Okay, we better be able to check whether the proof is legitimate and the steps are followed correctly. And if we can prove something, then that thing better be true. We don't allow inconsistent proof procedures that would allow us to prove things that are not true. So the set of provable statements in number theory is Turing recognizable. In other words, the statements that we can make using first-order predicate logic and operations like plus and multiplication is Turing recognizable. And how can we know that? Well, we have a proof down here that we can enumerate all the provable statements. And since we can enumerate it, that makes it Turing recognizable. We can enumerate all provable statements. So if some statement is provable, we can eventually find out that it is provable by discovering the proof for it. So we just enumerate all possible proofs. And we can do that because we have a finite set of axioms. We have a finite set of rules of inference. Every proof is finite in length. Every formula is, of course, finite in length. So we can just start listing all proofs out. We can enumerate all proofs. And so if there's some statement that is provable, then we will eventually enumerate the proof for that statement. We will eventually find the proof for that statement. So the set of all provable statements in number theory is Turing recognizable. Now we come to the amazing incompleteness theorem. And it is this. Some statement in number theory is true, but not provable. Okay, we can call this statement psi. Some statement in the theory of this, okay, remember this is the set of all true statements. So some statement that is true of number theory will have no proof. And so I can kind of paraphrase this as even simple arithmetic contains truths that are inaccessible. Okay, we can't find proofs for them. The proofs don't exist. It's not a question of whether we find them, it's that they are true but not provable. And we don't need much more than addition and multiplication in order to get there. Okay? So another way to paraphrase this is number theory is way deep. We're dealing with things that are true but not provable. So this is very interesting, very fascinating to think that some statements are out there that are true, but we can't prove them. They can never be proven. Even if we search enough, they can't be proven. And so now let's move into the proof of why this is true. Okay, let's move into the proof of this extraordinary result. Here's our proof. It's by contradiction. The theorem says that there are some true statements that are not provable. So let's assume that the opposite is true, that all true statements are provable. So if we want to know whether a statement is true or not, here's an algorithm that will decide the truth of a statement. Okay. And of course we know that the set of provable statements is undecidable. But here, let's go forward here. What we do is we take a look for a proof of the statement, and we look for a proof of its negation. I think I called it psi on the previous page, but here we're back to phi. But in any case, we look for a proof of the statement, and simultaneously we search for a proof of its negation. Now either the statement is true or it's false. If it's true, then this statement is true, and if it's false, then this statement is true. So we assume that all true statements are provable, so there must be a proof for either this or this. One of these two statements is true. Eventually, we'll find a proof of either one or the other. Either we'll find a proof of phi or not phi. One of these has to be true, and we're assuming that all true statements are provable, and we can enumerate all proofs, so eventually we'll find a proof of either this one or this one, because either this is true or this is true. But we already know that number theory is undecidable. Okay, so we can't decide the truth of these statements. We can't find a proof of these, so we can't decide the truth of statements. Okay, we know that the set of true statements is undecidable, but we've just figured out a way to find the truth of a statement. Assuming all true statements are provable, then all we have to do is find a proof, and we can enumerate all the proofs for the statement and for its negation. So therefore, we can find a proof that it's true or the proof that it's false. But we know that number theory is undecidable. That is, the set of true statements is undecidable. We can't decide the truth of statements. So therefore, we've reached a contradiction, and that's the proof. So what this is telling us is that there are statements out there that are true but not provable. So what might such a statement look like? Well, here is one example. Imagine the following sentence as a statement of fact. This sentence is not provable. Well, if that statement is proved, it would not be true. So it can't be provable. Okay, this sentence is not provable is correct if we can't prove it. Okay, if we can prove it, then the sentence is false. So what Godel did was figured out how to encode such a statement as this into a statement in number theory. Okay, it's a very clever idea, but we can symbolize the encoding as psi sub unprovable. It's an encoding of this sentence, or a sentence like this, into a statement in number theory. And then we can ask, is it true? Well, if we can find a proof of it, then it's a contradiction. Okay, if we find a proof that it's true, then it's not true and our system is not consistent. Okay, if we could find a proof that this sentence is not provable, then that sentence would be false, and we've just found a proof of something that's false. So therefore, a proof can't exist for it. It must be true, but not provable. Okay, therefore it must not be provable, and therefore it must be true. So there is an instance of a statement that is true but not provable. And the fact that he encoded it into an arithmetic statement in number theory is where the cleverness comes in part. Now, you might look at this sentence and say, well, wait a minute, this is kind of a suspect thing to start with because it says this sentence is not provable. And so there's some sort of self-reference here. And is that legal? Is that legitimate? Can a sentence refer to itself? And maybe this is not even a well-formed sentence. But this is the beauty of the recursion theorem. Okay? The statement contains the words this sentence and refers to itself. But the recursion theorem essentially shows us that this sort of a statement is okay. It's legal. It's okay for a sentence to refer to itself. And so that's Godel's incompleteness theorem. It says that there's some statements in number theory that are true but that can't be proven. And that's a very important result. And so it's just fascinating.